Hello, welcome to the brand new section Metaprogramming. In this section, we will first see representation of a Julia program, then symbols, following that quoting, interpolation, evil function, then very important macros, and lastly metaprogramming with data frames. Now we move on to the first video of this section that deals with representation of a Julia program. Here we will get started with representation of Julia program. You will study the life of a Julia program and how it is actually represented and interpreted by Julia. You will also learn what is meant by a language expressing its own code as a data structure of itself. This video will act as a foundation for learning about the concept of metaprogramming and how Julia uses it for generating code. To get started with this section, you must simply have your Julia REPL up and running. Firstly, it is very important to know that every Julia program starts out as a string. Let's consider a short program for adding two variables as our Julia code, and use it to learn how Julia interprets programs. Let us type code equals to a plus b. It would look like this. Now, if you parse the preceding string code, it would return an object of type expression. Let's check it by actually parsing an example Julia program and checking for its type. Check equals to parse code. The output would be like this. We will learn more about the preceding notation later. Now, the parse string check is a Julia expression. You can verify that by checking the type of check using the type of function in Julia. Type of check. This will turn EXPR as an output, which is nothing but a short form of expression, which is what the current type of check is. So, the expression object consists of three parts: the head, the arguments, and the type. Each argument can be checked in different ways. The head of the expression can be checked using check.head. This returns call as an output. The type of the expression can be checked by check.typ. This returns any as the output. The type can either be given by the user in the program or inferred by the compiler, as Julia is a dynamic programming language. The argument of the expression can be checked using check.args. This returns an array of the arguments used in the code. The output looks like this. The arguments can be symbols such as plus or minus, literal values, or maybe other expressions. So, from this process, you can clearly infer that the code in Julia is represented as a data structure of the language itself internally. Now, let's take a look at the dump function, which gives a nice annotated display of the check expression. This can be done by entering the check variable into the dump function. It can be done using this, dump check. This should return an output listing the arguments, types, and the head of the expression in an annotated manner. The output would be something similar to this. So you have seen how Julia interprets code as data structures with a simple example. In fact, you can try the same with a more complicated example. This is how to do it. Firstly, assign the statement like this. A plus B into C divided by 6. This is how it would look along with the output. Then parse the program. Check equal to parse code. Along with the output, it would look like this. Now, check the type of check. This is how it would look. Finally now, use the dump command to take a look at the content of the expression. Dump check. Oops, let me correct the typo. So, this is how it would look. Now let us see how it works. The entire purpose of metaprogramming is to make Julia express its own code as a data structure of itself. One of the main advantages of this is that complex steps and sophisticated and repetitive tasks can be automated through code generation. So, to make this possible, every Julia program starts out as a string so that it can be parsed and expressed later. Then, the string that is our program is parsed as an object, and that parsed object is called an expression. Now, the expression object is a store for all the details regarding to parsed string, which is our program. We will later explore how and where the details of the program are stored in the expression objects and how to make use of them. The conversion or the parsing step, where a piece of code is parsed as an expression object, can be checked by checking their type. As mentioned, the expression object has complete details about the string, which is our program. This includes the head, type, and argument parts, which would be studied in detail in the next video. So, for an annotated view of the details in the expression objects, the dump function comes in very handy. It unfurls the details in a nested manner to make understanding complex objects easy. If you want to know more about the concept of metaprogramming, visit stackoverflow.com. For a better understanding of S expressions, which are used to parse the expressions, go through this link. Great! In this video, we started with representation of Julia program, then we saw how to actually do it, then learned how it works.